Hello students, welcome back to the subject of fluid mechanics. We are learning basic properties of fluid in lecture number 11. I welcome all of you. Myself Praveen Chadav, assistant professor in mechanical engineering. Now in last lecture we have discussed about viscosity and we have solved some problems related with the viscosities. The learning objective of today's lecture is to know the importance of fluid mechanics and to know the various properties of fluid mechanics. After completion of this lecture, you will be able to know the basic content of fluid mechanics as well as you will be able to explain the basic properties of fluid mechanics. So in last lecture, we have discussed about the viscosity and we have discussed about some problems related with the viscosity and unit conversion in a viscosity. In today's lecture, we are going to focus on some other properties, fluid properties like compressibility, surface tension, vapor pressure, capillarity and cavitation. Out of these few properties you have already studied in 11th, 12th science also, like a capillarity and surface tension phenomenon. Because in a day-to-day life also we are observing similar kind of properties like a capillarity action and surface tension phenomenon. So we will see in a detail related with these properties. So what is compressibility and bulk modulus? Bulk modulus is defined as the ratio of compressive stress to volumetric strain. So for that purpose, consider a cylinder fitted with a piston as shown in figure. So this is one cylinder fitted with the piston having pressure P on the piston, and suppose A be the volume of cylinder and it is displaced to a distance dA. So due to that the pressure increases to P plus dP and the volume of gas decreases from V to V minus dV. So since pressure increases, piston moves forward, ultimately it will result in a decrease in volume. Okay, so here then increase in pressure is nothing but dP and decrease in volume is nothing but dV. Then volumetric strain is nothing but dV by V, change in volume with respect to the original volume, that is nothing but the volumetric strain developed. Now here volumetric strain is given in a negative signatures, that is minus dV by V. What minus sign indicates? Minus sign gives that volume decreases. Suppose opposite to that, if piston moves in a backward direction, then there will be the increase in volume. So the volumetric strain should be dV by V. At that time it may be a positive sign. So here it is negative because volume goes on decreases with increase in pressure. So bulk modulus can be given as K is equals to increase of pressure divided by volumetric strain. So it is nothing but dP divided by dV into dV by V. So bulk modulus can be given as K is equals to minus dP by dV into V. That is, bulk modulus can be defined as change in volume with respect to change in pressure with respect to change in volume and product of its product with respect to velocity V. Now what is compressibility? Compressibility is reciprocal of bulk modulus. Compressibility is reciprocal of bulk modulus. So again here bulk modulus is the ratio of compressive strength to the volumetric strain. So compressibility is nothing but ratio of volumetric strain to the compressive stress. So it works as a reciprocal of bulk modulus. Now adhesion. Adhesion, it is called as a property of fluid by which particles of different fluids or solid and fluids are attached. And capillarity is mainly due to adhesion property of fluid. So for that purpose you can take a simple example, or you might have performed such a kind of experiment sessions also. If in a bathtub you have inserted one pipe or transparent pipe, then you will observe that the water level inside the pipe is above the water level in the bathtub. Why it is happens so? It is the reason of capillarity, or it is the reason of adhesion. The capillarity action we have seen many number of times without any pressure, without any external forces also. Fluid shows different levels. So this is the effect of adhesion. And cohesion is the another property by which particles of same fluids are attracted towards each other, and it is called as a surface tension, and it is mainly due to cohesion property of fluid. So adhesion and cohesion are the two properties of fluid which are responsible for capillary action and surface tension respectively. Sorry. So surface tension is defined as the tensile force acting on the surface of fluid in a contact with a gas or the surface between two immiscible liquids, such that the contact surface behaves like a membrane under the tension. So here it is denoted by Greek letter sigma, and SI unit of surface tension is Newton per meter, and MKS unit is kg per meter. So here it shows the surface tension phenomenon when the free surface comes. Suppose the molecule A is free and it is inside the fluid, then it has the attraction from all sides with equal intensity. But when it comes in a direct contact with the surface, it shows the attraction towards only in downward direction. So over the fluid, unknowingly it creates a small membrane, and due to the surface tension phenomenon only, we can say water droplets are produced due to the surface tension phenomenon. Again, floating of lip over the water surface is again example of surface tension, where due to the surface tension only over the water, that lip is floating. So here some examples has given, specially walking on a water. A small insects such as the water sliders can walk on water because of their weight is not enough to penetrate the surface. So here water surface creates a surface tension, due to which one small membrane is developed, just like one layer is developed, and over that insect can move easily. See, this phenomenon we have used by the people's, it is the common phenomenon of surface tension used for many applications also, just like in a design of ship. So here it floats over the water. Then floating of needle, a carefully placed small needle can made to float on the surface of water, even though it is so several times dense as water. If the surface is agitated to break up the surface tension, then needle will quickly sink. So I will tell you one example. When you are a child, you might have prepared paper boat, which is floating over the water, or some kind of equipments which are floating over the water. If you are immerse it with some high intensity, for example, मी सांगेन तुम्हाला की एखादी वस्तू तुम्ही असं वरून खाली टाकलात जोरात पाण्यामध्ये, it will automatically dump down. 100% it will sink in the water. But if you keep it very thoroughly over the layer of water without applying any additional force, then for some period of time, it may get float over the water. This is due to the surface tension. If it is dumped from above side with some certain height, then it will be sink down inside the water. Then naturally observing surface tension phenomenon example is droplets. Now the rainy season is going on, so you may observe outside the home also, over the grass, you may observe the droplets. The surface tension is responsible for the formation of spherical shape of liquid droplets, through which easily deformable property of water, but water is developed in terms of spherical shape. So if a very small amount of rain falls down, then observe outside over the grass. You may observe the small water droplets were there which are developed. Now, what is the natural phenomenon of water? It is liquid. It has to be an flow, but even though the droplets are formed, these droplets are formed because of only cohesive force of the surface layer, only due to the cohesive force of surface layer. So these are some examples of surface tension. And the another examples of capillary actions, as I said, you can perform the experiment at your home also. Take a small needle type or very small diameter pipe and insert it in a water tank. Then you may observe that the level of water inside the needle is much more above the level of water in a tank. Why this happens? Because due to the adhesion property of fluid, it tries to be adhere with the surface in which it is inserted, and since its cross sectional area is very less, it tries to be move in a upward direction. So it is called as a capillary action. I think this both phenomenon you have studied in 11th and 12th science also, because both are in engineering physics, and same phenomenon we are going to use that here. Now, expression for surface tension on the droplet. The tensile force due to surface tension will be acting. Let sigma be the surface tension of the liquid, P be the pressure intensity inside the droplet, and D be the diameter of droplet. Now consider this is a droplet which is shown in a figure A in a circular spherical format. B is nothing but the cut section of droplet, which shows stress sigma, surface tension sigma is acting over the periphery of the droplet, and C is nothing but the pressure force which is acting inside the droplet, opposite to the shear stress force sigma. If the pressure inside the droplet is high, then surface tension will be gets minimized and water will be flowed. So the droplet having half force, opposing force sigma, surface tension force sigma, over which opposing force, pressure force is acting. Now, with respect to this, tensile force due to the surface tension around the circumference of cut portion of the figure is equals to sigma into circumference of this droplet. So circumference is given as pi d. So it is half side of force, and remaining force is acting over the cross section of this droplet, which is the pressure force. So pressure force P is acting on pi by 4 d square as a cross sectional area of surface. So these are two, according to equilibrium condition, these two forces are equal. So we can write that P into pi by 4 d square is equals to sigma into pi d. So pi will get cancelled, d will get cancelled, remaining is pi d by 4 is equals to sigma. So we can say that sigma is equals to pressure force P is equals to 4 times sigma divided by diameter of droplet. Now surface tension on hollow bubble. Now consider a hollow bubble like air bubble, because it is required to consider hollow bubble because over the bubble the pressure force acting in a opposite direction. Here the pressure force acting is in a opposite direction, because inside the bubble it is hollow condition, but outside air acting pressure over the bubble. So that's why we have considered the hollow bubble condition. Now a hollow bubble like a soap bubble, air has two surfaces in contact with air, one inside and other is outside. So surfaces are subjected to the surface tension 2 times. So P into pi by 4 d square is equals to 2 times sigma into pi d. So P can be given as P is equals to 8 times sigma divided by d. Now surface tension in a liquid jet. Consider a liquid jet of diameter d and length L as shown in figure. Now instead of droplet, here we have considered a jet. So jet figure is shown in a figure A having length L. Now if it is cut at this mid section, then have over the periphery of this jet circumferential stress, surface tension sigma is acting. So pressure intensity inside the liquid jet and above the inside pressure is as shown in figure. Now the equilibrium of semi-jet, we have force due to the pressure is equals to P into area of semi-jet. So P into L as a length into D is nothing but the diameter. The pressure force is acting, which is opposite to the sigma force, and sigma force is acting over the sigma into 2L, both side of length. Here in a figure itself it is observed, this is one length, this is second length, over which circumferential stress sigma is acting. So force due to the surface tension is sigma into 2L, and force due to the pressure opposing to that acting over this area. So again equating the equations, P into L into D is equals to sigma into 2L. So again here L will get cancelled, and the remaining is P is equals to 2 sigma divided by D. Okay, so for water surface purpose, the formulas are: for water droplet, pressure P can be given as 4 times sigma divided by D. For soap bubble, formula can be given as P is equals to 8 times sigma divided by D, and for liquid jet, formula is given as P is equals to 2 times sigma divided by D. Now come to the capillarity action. Here in the capillarity, it is defined as phenomenon of rise or fall of a liquid surface in a small tube having small tube relative to the adjacent general level of liquid when the tube is held vertically in the liquid. So we discussed already in the capillary action, generally what I observed is water is moving in upward direction. So we discussed related with the rise in capillary action level only, but sometimes it may get falls also. The rise of liquid level is known as capillarity rise, whereas fall in liquid level surface is known as a capillarity depression. This increase or decrease action is taken place due to the attraction or adhesion between the wall and tube, and liquid molecule is strong enough to overcome the mutual attraction of the molecule and pull them up the wall. Hence the liquid is said to be wet the solid surface. So in the capillary action, it is expressed in terms of centimeter or mm of liquid with which it is rising. Its value depends upon the specific weight of the liquid and diameter of the tube and surface tension of the liquid. Now angle of contact. Here some actions are shown at here where angle of contact is acute. The angle of contact is very acute due to the small size, and when cohesion is greater than adhesion, smaller than adhesion, there will be the decrease in water level, and if it is greater than, then there will be the increase in water level. So here are some examples of capillary action. Liquid rise inside a straw. That is the best example. When we are drinking a cold drinks, inside that if you are inserted a straw, water level will rise. Then paper towel absorbing water or paper napkin which we are using, it absorbs the water. Then plant roots absorbing water from the soil. Sponge, tissue paper absorbing ink, draws ink to the tip of fountain pen. So these are the some best examples of capillary action. Now expression for capillary rise. Consider this is the capillary which is inserted in a liquid, due to which liquid is rise up to the height h. Let theta be the angle of capillarity due to the surface tension sigma. Then specific weight of water can be given as W is equal to weight of liquid divided by volume of liquid. Weight of liquid can be given as a volume of liquid into specific weight. So specific weight W is nothing but rho into G. Now weight of liquid of height with in the tube is given as area of tube into H is nothing but height up to which water level is raised into rho into G. So it is nothing but pi by 4 d square H into rho G, where rho is nothing but density of liquid. So vertical component of the surface tension force is given as sigma is equals to circumference into cos of theta. So sigma into 2 pi d into cos theta is nothing but vertical component of the surface tensile force. So by considering equilibrium conditions, pi by 4 d square into h into rho into g is equals to sigma into pi d into cos theta. So h can be given as sigma into pi d into cos theta divided by pi by 4 d square into rho g. So pi will get cancelled, 4 will be goes on upward direction, so h can be given as 4 times sigma cos theta divided by rho gd. So the value of theta between water and clean glass tube is approximately equal to 0, and hence cos theta is equals to the unity. Then rise in water is given as h is equals to 4 sigma divided by rho g d. Now expression for capillary fall: if the glass tube is dipped in mercury, the level of mercury in the tube will be lower than the general level of the outside liquid. So here h will be the height of depression in tube. Then the equilibrium of two forces are acting on the mercury inside the tube. First one, due to surface tension acting downward direction, is equals to sigma into pi d x cos theta, and second force is due to the hydrostatic force acting upward and equal to the intensity of pressure at depth area. So for this angle purpose, again specific weight, we know that W is equals to rho into G. So weight of liquid in the tube can be given as pi d square H rho G, and volumetric expression is nothing but sigma into pi d cos theta. Again equating the both equations, we will get H is equals to 4 sigma cos theta divided by rho G d. Now here theta value of mercury is 128 degree. So due to that, it will be shows a negative angle. So capillary rise or depression can be given with the common formula H is equals to 4 sigma cos theta divided by rho GD, where sigma is nothing but surface tension, theta is nothing but angle of contact between the liquid and glass tube. The value of theta between the water and clean glass tube is approximately equals to 0, and hence cos theta is equals to unity. Then rise of water is given as value of theta for mercury and glass tube is 128. Where we are using capillarity action, capillarity is essential for lubricating oil spread easily on all parts because of their low surface tension. Cotton dresses are preferred in summer because cotton dress have fine pores which acts as capillary for sweat. Then dirt get removed from detergent are added while washing clothes because surface tension of water is reduced. So these are some examples. Then vapor pressure is the next property. So I think we will stop at here, or we'll see at least vapor pressure. So vapor pressure is nothing but the pressure developed due to the vapor. Temperature increases the amount of vapor generated by liquid in a closed container. This occurs because of the liquid gains kinetic energy. The molecules can overcome the intermolecular forces of attraction and that are prevalent in the liquid phase. So vapor pressure increases with increasing temperature. And last part is the cavitation. Cavitation is the phenomenon of formation of vapor bubbles of a flowing liquid in a region where the pressure of the liquid falls below the vapor pressure, and sudden collapsing of those vapor bubbles on the region of higher pressure. So this is the reason why cavitation is generated. I think this part also you have studied in a diploma. Here, when the water is flowing through the venturimeter, due to the sudden decrease in cross-sectional area, vapor bubbles are formed because here the pressure of the liquid falls below the vapor pressure, and pressure is converted into velocity, and after that again at increase in area velocity gets dropped and pressure is increases. So when vapor bubble collapse and a very high pressure is created, the metallic surface above which the liquid is flowing is subjected to this high pressure, which causes pitting action on the surfaces. Thus cavitations are formed on the metal surface, and hence the name is cavitations. So this phenomenon called as a cavitation phenomena. The major places where cavitation occurs are pumps, propellers, turbines, or at restrictions in a flowing liquid. Cavitation is a significant force of we are in some engineering context also. So here some examples of propeller of shaft have turbine has been shown where cavitation is taken place due to the sudden drop of pressure and sudden increase in pressure due to the air bubbles. Okay, so this is about these properties of fluid. In next lecture we will see some problems and remaining properties. Thank you very much.